Hi, I'm Rebecca. I'm going to explain you about series solutions near an ordinary point. We now consider methods of solving second-order linear differential equations when the coefficients are functions of the independent variable. I mean, p of x, the second derivative of y with respect to x plus q of x dy dx plus r of x y, and this is equals to 0, and an ordinary point is a point let x sub 0 such that p of x sub 0 is different from 0. This means that you evaluate the function when x is equals to x sub 0 and everything is okay. On the other hand, a singular point is a point x sub 0 such that p of x sub 0 is equals to 0. In this case, there are problems. And we now take up the problems of solving differential equations in the neighborhood of ordinary and ordinary point, x sub 0. We look for solution of the form of a series of power. That is, y is equals to a sub 0 plus a sub 1 x minus x sub 0 plus point plus a sub n x minus x sub 0 to the power of n, and this is equals to a series which starts when n is equals to 0 until infinity a sub n x minus x sub 0 to the power of n. And we assume that the series converges in the interval modulus of x minus x sub 0 less than rho, when rho is the radius and rho is greater than 0. Well, I'm going to do an example. This example asks us to find a series solution of the equation y prime prime plus y is equals to 0. This is an easy example because the coefficients are constants. In this case, p of x is equals to 1, would be this. Q of x is equals to 0. Remember that the q of x is the term that is with y prime, and r of x is equals to 1. So, all points in the interval minus infinity, are ordinary points, and I'm going to choose the easiest one, which is 0. X sub 0 is equals to 0. We look for solution of the form of a series of power would be y is equals to a sub 0 plus a sub 1 x plus a sub 2 x to the square plus point, and this is equals to a series which starts in n is equals to 0 until infinity a sub n x to the power of n. And we assume that the series converges in the interval modulus of x less than rho. The derivative of y would be y prime is equals to a sub 1 plus 2 a sub 2x plus point, and this is equals to a series which starts in n is equals to 1 until infinity n times a sub n to the power of n minus 1. Isn't it? Well, and the second derivative of y would be y prime, and this is equals to 2 a sub 2 plus point, plus n times n minus 1 times a sub n to the power of n minus 2. And this is equals to series 2, which starts in this case when n is equals to 2 until infinity, n minus n minus 1 a sub n times x to the power of n minus 2. And well, I have the solutions y and y prime, and I'm going to substitute y and y prime in my differential equations. So we have the series which starts in n is equals to 2 until infinity n minus 1 a sub n x to the power of n minus 2 plus the series which starts in n is equals to 0 a sub n times x to the power of n, and this is equals to 0. And to combine the two series, we need to rewrite them with the same power. And to do that, I'm going to do an index change, which is k is equals to n minus 2, and solving for n would be n is equals to k plus 2. So this is my index chain, and we have I'm going to do my index change for this series. So if this series starts when n is equals to, my new series starts when k is equals to 0, because if I substitute 2 in n, well, it would be 0. So my new series would be infinitive k, which starts in 0, and I have n. And who is n? K plus 2. K plus 2 times n minus 1 would be k plus 2 minus 1. A sub n would be a sub k plus 2, and x to the power of n minus 2 would be k plus 2 minus 2. And we have the series which starts in k is equals to 0 until infinitive, k plus 2 times k plus 1, a sub k plus 2 times x to the power of k. And remember that the index are silent, so I can substitute n for k in my new series. Then my new series, which starts in n is equals to 0 until infinitive, n plus 2 times n plus 1, a sub n plus 2 times x to the power of n. And we realize that now this series and the other one have the same power, and both start at the same number. So we have this series in my differential equations would be this plus this so we can take this out as a common factor, and the series which starts in n is equals to 0, x sub n, And as a common factor, we have n plus 2 times n plus 1 times a sub n plus 2 plus a sub n, and this is equals to 0. And this is the recurrence relation. I can find the term of a sub n evaluating one by writing the recurrence relations first for n is equals to 0, then for n is equals to 1, and so forth. Well, for the even-numbered coefficient, we have when n is equals to 0, and if n is equals to 0, we have n plus 2 would be 0 plus 2, which is 2. N plus 1 would be 0 plus 1, which is 1, times a sub 2 plus a sub 0, and this is equals to 0. And solving for a sub 2 is equals to minus a sub 0 over 2 times 1, and 2 times 1 is 2 factorial, okay? And when n is equals to 2, we have in my recurrence relation n plus 2 would be 2 plus 2, which is 4, times n plus 1 would be 2 plus 1, which is 3, times a sub 4 times a sub 2, and this is equals to 0. And solving for a sub 4, a sub 4 is equals to minus a sub 2 over 4 times 3, and I can substitute a sub 2 with that. So, minus 4 times 3, a sub 2 is minus a sub 0 over 2 factorial. And 4 times 3 times 2 factorial is 4 factorial. A sub 4 would be minus positive minus times minus is a positive sign, so a sub 0 over 4 factorial. This result suggests that in general, if n is equals to 2k, then a sub 2k is equals to minus to the power of k a sub 0 over 2k factorial, when k is equals to 1, 2, 2, 3, and so forth. Similarly, for the odd-numbered coefficient, odd-numbered coefficient, we start in n is equals to 1, and we look at the recurrence relations. N plus 2 would be 1 plus 2, which is 3, times a plus 1 would be 1 plus 1, which is 2. A sub 3, because 2n plus 1 would be 3, plus a sub 1, and this is equals to 0. And solving for a sub 3, we have a sub 3 is equals to minus a sub 1 over 3 factorial. And when n is equals to 3, we have, my recurrence relation is n plus 2 would be 3 plus 2, which is 5. 5 times 4 times a sub 5 plus a sub 3. Isn't it? So, solving for a sub 5, we have a sub 5 is equals to minus a sub 3, 5 times 4, and I can substitute a sub 3 with that. So, we have a sub 1, minus times minus is a positive sign, and 5 times 4 times 3 factorial is 5 factorial. These results suggest that, in general, if n is equals to 2k plus 1 for the odd number coefficient, then a sub 2k plus 1 is equals to minus to the power of k over 2k plus 1 factorial a sub 1. where k is equals to 1, 2, 3, and so forth. Well, for the even number coefficient and odd numbered coefficient, and we realize we can write the terms as a series, so we can write the solution as a series. Therefore, I have y is equals to a sub 0 times the series which starts in n is equals to 0 until infinity minus 1 to the power of n over 2n factorial x to the power of n. And this is for the even number coefficient plus the series which starts in n is equals to 0 until infinity minus to the power of n over 2n plus 1 factorial times x to the power of n plus 2n plus 1. And this is for the odd number coefficient. And this is our solution as a series.